When you interact with an AI today, you're used to a specific rhythm, the rhythmic, typewriter-like delivery of text. It feels fast, but in the world of silicon and light, it's actually a crawl. We've hit a wall that no amount of traditional GPU power can easily climb over. This isn't a software problem, it's a physical one. To generate a single word, a model like GPT-4 has to move trillions of parameters from memory into a processor, do the math, and send it back. And it has to do this for every single token, one after another. In a standard data center, these chips are separated by inches of copper and miles of fiber optic cables. Even at the speed of light, that distance creates a delay, a latency, that makes real-time human-speed software generation impossible. Until now. Engineers call this the memory wall. It's the gap between how fast a processor can think and how fast the memory can feed it the information it needs. Imagine trying to read a book, but you have to run to a library in the next town for every single word. Traditional GPU clusters try to solve this by stacking more chips together, but this actually makes the communication problem worse. The more chips you add, the more time they spend talking to each other instead of doing the actual work. It's a classic case of too many cooks in the kitchen. To break through, we didn't just need faster chips. We needed to rethink the entire geometry of the computer. We needed to stop thinking about clusters and start thinking about the wafer itself. This brings us to the engineering marvel behind GPT 5.3 Codex-Spark. Instead of using thousands of small chips, it uses the largest piece of silicon ever made. It's a transition that changes everything we know about how AI models are served to the world. By placing the entire neural network on a single continuous piece of silicon, we eliminate the need for external wires. The memory is no longer in the next town. It's living right inside the processor's house. This is the death of the memory wall. The result is a system that doesn't just run AI, it breathes it. We're talking about a leap in efficiency that allows for speeds we previously thought were physically impossible for models of this complexity. To understand the scale of this change, look at the bandwidth. A typical high-end GPU cluster might move data at a few terabytes per second. The Wafer-Scale Engine moves it at 21 petabytes per second. That's a difference in scale that's hard to even visualize. This isn't just a linear upgrade, it's a phase shift. It's the difference between a bicycle and a supersonic jet. When the model can access its own weights nearly instantly, the thinking process becomes a continuous flow rather than a series of stutters. This engineering breakthrough is what allows Codex-Spark to reach the holy grail of inference, 1,000 tokens per second. That is the speed required to make the AI feel less like a tool and more like an extension of your own mind. But building something this large presents a massive engineering challenge: yield. Usually, if a single speck of dust hits a silicon wafer during manufacturing, the chip is ruined. On a wafer this size, a speck of dust is a statistical certainty. Cerebras solved this with a brilliant bit of redundancy. They built the wafer with thousands of extra cores. If one part of the silicon is defective, the system simply routes around it, like a GPS finding a new path when a road is closed. This fault-tolerant design is what makes wafer-scale computing viable. It's a masterclass in working with the imperfections of physics to create something that feels perfect. And it's the foundation for the next era of software development. To truly appreciate the wafer-scale engine, you have to look at the numbers. We are talking about 4 trillion transistors. For context, the processor in your laptop has about 20 billion. This is a scale of complexity that borders on the unfathomable. Every square millimeter of this silicon is packed with 900,000 AI-optimized cores. Because they are all on the same piece of silicon, they can communicate with each other with almost zero lag. It's like a city where every building is connected by a teleporter. This massive fabric of compute power is what allows GPT 5.3 to process information in parallel at a scale no GPU cluster can match. It's not just more power, it's more efficient power. The secret sauce here is the SRAM, Static Random Access Memory. Unlike the HBM memory used in GPUs, which sits on separate chips, SRAM is etched directly into the logic of the wafer-scale engine. It is the fastest memory in existence. Because the memory is right there, the processor doesn't have to wait for data to arrive. In a traditional system, the processor spends up to 90% of its time just waiting. On the wafer, it spends 100% of its time working. This design choice is expensive and difficult to manufacture, but for a model like Codex-Spark, it's the only way to achieve the throughput needed for real-time interaction. It's engineering without compromise. But with 4 trillion transistors comes a lot of heat. Powering and cooling a single giant chip is an engineering nightmare. You can't just use a fan. You need a sophisticated liquid cooling system that touches every inch of the silicon. The cooling system has to be as precise as the chip itself. It uses a manifold that distributes water evenly across the entire surface, ensuring that no single core gets hotter than its neighbors. It's like a radiator for a supercar, but shrunk down to the size of a pizza box. This thermal engineering is just as important as the silicon design. Without it, the wafer would melt itself in seconds. It's a delicate balance of power, data, and thermodynamics. Then there's the power delivery. Delivering 20 kilowatts of power to a single chip is like trying to power a whole street through a single outlet. It requires a massive power distribution system that sits directly behind the wafer. This power isn't just dumped in, it's carefully regulated by thousands of tiny voltage regulators. They ensure that every one of those 4 trillion transistors gets exactly the right amount of energy at the right time. It's a symphony of electricity. The engineering required to keep this giant alive is just as impressive as the AI it runs. It's a self-contained ecosystem of compute, memory, power, and cooling, all working in perfect harmony. So why go through all this trouble? Because when you eliminate the memory wall, you don't just get a faster AI, you get a different kind of AI. You get a model that can think as fast as you can talk. This 1,000 token per second speed is the threshold for vibe coding. It's the point where the delay between an idea and its execution disappears. But to understand that, we have to see what it looks like in practice. The engineering of the wafer-scale engine is the how. Now, let's look at the why and how it's about to change the way every piece of software on Earth is written. Instead of typing lines of code, you're just talking. You describe a feature and it appears. You don't wait for a compile step. You don't wait for a deployment. It just happens. This is vibe coding. This is only possible because of that 1,000 token per second speed. At that rate, the AI can generate entire files, refactor databases, and update UI components in the time it takes you to finish a sentence. The feedback loop is instantaneous. It's called vibe coding because the barrier of syntax is gone. You're no longer a translator for the computer, you're an architect of intent. The vibe of your idea is what matters, and the wafer-scale engine handles the rest. But the implications go far beyond just making coding easier. When AI can generate software this fast, the software itself becomes dynamic. It can change its own interface based on who is using it in real time. We are moving away from static apps toward living software. Your phone could generate a custom tool for a specific task you're doing right now and then discard it when you're done. The cost of creating software is effectively dropping to zero. This shift is forcing the entire industry to move away from general-purpose GPUs towards specialized AI hardware. If you want to play in this league, you need silicon that was born for this specific task. Of course, there are trade-offs. This extreme inference speed requires massive amounts of power and specialized data centers. You can't run a wafer-scale engine in your basement. at least not yet. It's a centralized power for a decentralized future. There's also the question of control. When software is generated at 1,000 tokens per second, how do we ensure it's safe? The engineering challenge of the next decade won't just be about speed, it will be about steering. But for now, the engineering community is focused on the pure, breathtaking potential of this technology. We have finally broken the memory wall, and the view from the other side is incredible. We are seeing the birth of a new stack. At the bottom is the wafer-scale silicon. In the middle is the Codex-Spark model. And at the top is the human voice. It is the shortest path between a thought and a reality that has ever existed. This isn't just about efficiency. It's about the democratization of creation. When the technical barriers of coding are removed by sheer brute force engineering, the only limit left is your imagination. The transition to specialized hardware like the WSE3 is the final piece of the puzzle. It provides the raw, unbridled speed that makes the magic of AI feel like a natural law of the universe. Next time you use an AI and the text appears instantly, remember the dinner plate-sized piece of silicon making it possible. Remember the trillions of transistors and the petabytes of data moving across a single wafer. The memory wall was a barrier for 40 years, but engineering ingenuity finally tore it down. We've entered the era of the silicon giant, and the software world will never be the same. The future isn't just coming, it's being etched into silicon right now, one wafer at a time. And the most exciting part? We're just getting started.